Hi class, this video is going to help with 11.1 and what we're doing in this section is the first derivative and its graph. Okay, so when I refer to the first derivative, I'm actually referring to just doing the derivative of your function. So we've been doing that for a while. But what does it tell me about the graph of the original? So you see my little chart here. And we can see that if the derivative is positive, so if you have a positive slope in that first derivative, then you're increasing on the original graph. Okay? If it's negative, then you're decreasing on the original graph. So I can take the derivative and it will tell me whether the original function was increasing or decreasing. All right, so here's kind of the idea. I also added the tangent line of the tangent line slope is positive, right? At that certain point, which we've looked at quite a bit. So the tangent line, we get the slope from the derivative, and that means it's positive if it's increasing. So positive, positive, negative, decreasing, negative. So what we're gonna do, this is kind of our process for this. We're gonna find critical values. And use test points to see where you're increasing or decreasing. So to find our critical values, what we're going to do is we're going to let the derivative of the function equal 0 and solve. Okay? So that's kind of where we're going to start. We could also have something called a partition number. They're really the same thing. I'd never even heard the word partition until this book. And then I was like, I'm pretty sure I learned that in calculus, but critical values and partition numbers really are about the same thing. And what the partition number is where the x value where it's discontinuous, or basically what I want to think of is where it's undefined, where the function f of x is discontinuous or undefined. So a partition and a critical value are the same thing. We just have to look basically where is the original function. Does it have 0 in the denominator? Does it have a square root where you can't be negative, right? So we're looking at where we are undefined. Mostly what we do is where the denominator equals 0. And then we have to find the critical values as well. We'll find both those numbers and they will help us with where we switch from increasing to decreasing. So you can only switch from one to the other at each of these values. So it's either a critical value or an undefined value. So the other idea that we're going to kind of get that we want to put in our notes before we do some examples is something called your local extreme. If I have a graph and it maybe did something like this, go up a little, I just kind of, oops. It's like backward when I touch my camera, so I'm like, oops. Okay, so if I have something like this, just a random graph, if I have what we call a local max, it's going to look like this. And a critical value or an undefined, it's almost always a critical value, isn't it? I have to think about that. The critical value is a max or min. Okay, and this would be a local min. And you could also have like a critical value somewhere else, like over here, and it'd be like a hole in your graph, just a random hole. So I'm not saying every critical value or partition number is going to be a local max or local min, but it could be. And those are the only places where you're going to switch from increasing to decreasing, and then again back to increasing. Okay? It doesn't mean you do, but it's the only places you possibly can. Okay, so Can a partition number or critical value be a local max, local min? Yes, they can. Can a local max or min not be on a partition number or critical value? Nope, they only happen at those. So what we're going to do is we're going to look at a sign chart, and we're going to call this value right here is going to be at C. Okay, that's at C. Okay, if this is our X, that's C. So what I am saying is that if I am going from, if my derivative of my function is on a sign chart here, and here's my critical value, that'll normally be a number, maybe that's at 2, 5, who knows. If that critical value, if you go from negative and then you switch to positive, then that means you have a local minimum, okay? Because minus means decreasing. Hit that C value, which could be C, or probably should call them a different letter. But this would be a local min. Okay. If I'm looking again at that derivative, let's call this one negative C. And we're at that negative C value, whatever that is, and we started positive, we hit this one and we switch to negative, that is what we're going to call a local maximum. And hopefully this will make more sense once I show a couple examples. So it's a local min, local max. So what we're going to do is we're going to find these critical values. We're going to just put in some values into our derivative to see if it's positive or negative before and after. And that's the whole main idea. What's it going to tell me? It's going to tell me whether you have a local min or max there. Okay, let me show you a couple examples. Welcome to pause if I go too fast, and put these in your notes. I keep thinking my power is going to go off because my light is going up and down. Okay, so look at this first one. We know that's like our x squared, and that here is our local minimum, okay? This is my original function. Then if I looked at the derivative, then it's going to be negative, and then it's going to be a 0. That's our critical value, is a 0, because it's where the derivative equals 0, and then it's going to go to positive. Whoop, whoop. And that means it's a local minimum. Okay, that's our original. It goes up. That means it goes positive, negative. Here's our 0 at C. That is going to be a local maximum. So if we are doing our critical values and we're going along and we have this critical value here, we could be going along like this, and look, it's increasing and increasing. So our slope, or our derivative, is positive, positive. So just because you have a critical value doesn't mean you're going to change from increasing to decreasing or vice versa. And then look at this one, same as this one. It's decreasing and then it slows down a little, but still decreasing. So it's all negative on my derivative. Okay. Here's another one. This would be a great example of a spot where a function is undefined for the derivative. Okay. So we would call it ND, stands for not defined. It just is a partition number. It doesn't, you get it differently because it's where the derivative is undefined. But basically, see how this goes down? We could not draw a tangent line at that spot, so we can't get the derivative at that spot. So it's undefined, but we're basically going decreasing and then increasing, so that that partition number is still going to give me a local minimum, but there's just not a derivative at that actual spot. Okay? But again, it still changed directions from there. And we could have like a hole in our graph, another non-defined, but it stays decreasing on this one. So they're all negative for the derivative. Okay, so you can see my example here. I was going to rewrite it, but maybe I won't. Okay, so here is, I don't know why I say question or, oh, I guess I labeled them all, whatever. This is really problem number 1. Here is my original function. Yes, I can plug this into a calculator and look what it looks like. I don't want you to do that yet. I want you to look at this graph, and we're going to find our critical values and our undefined spots, our partition numbers. How are we going to do that? We're going to start with the derivative. Okay, so we start with the derivative because we're going to see where that equals 0. So the derivative of x to the third, you bring the 3 down, x squared. Okay, the derivative of this one, 2 times 6 is not 6. Yeah, I'm going to write this one on my own paper. I had a mistakey on it. Hold on. Okay, so this original function was x to the third minus 6x squared plus 9x plus 1. I'll have to remember to put a sticky note on that one. So first thing we want to do is we have to find the derivative to see where that equals 0 for our critical values. So we aren't going to have any undefined values because we don't have a denominator with an x. So that's great. We don't have a square root. I will definitely show you one with something, but let's just do the derivative. So this one would be 3x squared. 2 times 6, bring down the minus, is going to give me 12x. The x goes away, so I just have a plus 9, and the 1 goes to 0. Here is our derivative of the function. Now we need to see where this equals 0 to get our critical values. So 0 equals 3x squared minus 12x plus 9. And this is going to find our critical values. So far I have no partition because I don't have where anything undefined. All right, so from here, I'm probably going to have to crack out some of my factoring rules. I look at this and think, okay, well, I can get a 3 out of each of them. So that leaves me x squared minus 4x plus 3, right? That's going to factor pretty nicely, leaving the 3 outside. If we think about the 3 at the end, if we want to get a positive 3, and we want to get the negative 4. If we have 3 times 1 and they're both negative, it would multiply to positive 3, but it would add to the negative 4. So that's what we're going to factor into. X minus 3, x minus 1. Oh yeah, I just did my factoring wrong over here on my notes because the rest of it I got right. So I probably just wrote something down wrong. Someone stole my notepad. That's okay. All right, so from here, we now can see this doesn't have an x with it, so it is not going to give us a critical value. If it was 3x, then we would have a 0. But we really only have 3 and 1. 3 and 1 from those two here. So those are our critical values. So the next step we're going to do is we're going to do a sign chart, right? So we're going to have our 1 and our 3, and I want to go in order. 1 comes before 3. And we're going to know that these are both zeros, and we're looking at the derivative, okay? Basically, we're going to look at each section, which we've done before on greater than and less than, x squared type things. So we're going to do test numbers. Okay, and we're just going to see if it's positive or negative. So we're going to have our x value here, and we're going to look at our derivative of that value over here. So what is something less than 1? Well, 0. I like 0. So we're going to put 0 into our derivative and see if it's positive or negative. So we could use our factored derivative. That's probably the easiest, or the original. I mean, I guess it doesn't really matter. So you'd have 3 times 0 squared minus 12 times 0 plus 9. Okay, so 3 times 0 at 0, or 0 squared, excuse me, times that 0, 0, 0. So I get just positive 9. Okay, I don't really care about the number. What do I want is if it's positive or negative. Well, it's positive. So before the 1, right, we got positive. in between the 1 and 3. What's a number between 1 and 3? Well, let's do 2. So then we're going to have 3 times 2 squared minus 12 times 2 plus 9. All right, so what are we going to get with this one? Well, 12 times 2 is 24. 2 times, I don't know why I did to the 4th. I think I was thinking 4, but this should be just squared. So that's 12. So we're going to have 12 minus 24 plus 9. My 12 minus 24 is a negative 12 plus, it's going to give me a negative. See that it ends up being a negative? Okay, we don't really care about the number. You could write it out, that's fine. So we would go up and we'd say, all right, now it is a negative. So is this a local min or max? Because it does change. So it is 1. So if it's increasing positive and then switches to decreasing, is that a top or a bottom? It's a max. So this is going to be a local max. And we'll look at the graph in just a second. Last spot, we got to go maybe at the number 4 because it's above 3. So let's put in a 4. So we would have 3 times 4 squared minus 12 times 4 plus 9. 4 squared is 16. 3 times 16. I don't know why I can't think of that in my head right now, but 3 times 16 is what? 48. Minus 24 plus 9. I can see that's going to get me a positive. So here we're positive. So we changed signs again, but this time we were going, we were decreasing, then we switched to increasing. So is that a max or a minimum? This one's going to be a minimum. We went negative to positive. So write yourself some good notes on that. This is what we're looking for. So what would we say? Our answer would ask, you could be asked, the tangent line is slope is equal to 0 where? So the tangent line slope equals 0 at 1 and 3, the critical values. Tangent line slope, where does it equal 0? That's just derivative equals 0. We've seen it before, but it tends to be something we don't do a lot, so we tend to forget it. Okay, we're going to be asked increasing as well, and this is the big idea for this section. And where were we increasing? In that section, because those were both positive. So we're increasing from negative infinity to 0, and or union with 3 to infinity. And where were we decreasing? From 1 to 3. And we don't include those endpoints because at those specific spots, we're equal to 0. And again, tangent line equals, slope of the tangent line equals 0 at the actual 1 and 3. Okay, let's take a sec. And I'm going to open Desmos real quick. And I want to show you the graph of the original function. So let's look at that. So our original function was x to the 3rd power minus 6x squared plus 9x plus 1. Okay, here's my graph of my original. Now finding my derivative said we're increasing until 1. Isn't that what we got? Why did I think 3? Till 0. Oh, it is 1. I think I wrote it down as 0. Increasing. And I'm not sure why. Okay, let me bounce back to what I'm showing you. Here, I wrote this down as a 1, but when I wrote it over here, I wrote it as a 0 because I wrote this 0 here. So change this to a 1. You might have already noticed I did that mistake. I just caught it because I was like, wait, we didn't write that down. Okay, so a 1. Let me go back here. So we are increasing from negative infinity all the way to 1. Then we're decreasing from 1 to 3. Okay, we don't care about the y value. Just look at your x from 1 to 3. Then we're increasing again the rest of the way to infinity. So we can look at the original graph and it better match what we find using our derivative. Okay, you will have to show these steps on the exam or I will take away the points for getting it. You have to be able to do this with the derivative. That's the whole point.